Welcome back, everyone. I hope you're all doing great. In our earlier videos, we explored the basics of differential equations, what they are, the different types, and the various types of solutions they can have. Today, we're going to take that knowledge a step further and explore new concepts. This series is designed to build on what you've already learned. That's why we encourage you to watch the videos in sequence and take time to practice along the way. Remember, practice is the key to mastering mathematics, and consistent effort always brings success. There are many methods to solve initial value problems, each with its own strengths and applications. In this video, we'll focus on Picard's method, a powerful and systematic approach. Before diving into the solution process, it's important to understand how Picard's iteration method works. At its core, this method starts with a simple approximation and then refines it step by step to get closer to the true solution. Now, let's explore this process and see why it's both effective and widely used. The Picard iteration method is a systematic approach for solving differential equations. It's based on an iterative process, which means we start with an initial guess and refine it step by step until we get closer to the actual solution. This method is especially useful because it builds on the idea of approximating solutions, which is a core concept in mathematics and physics. Imagine you have a puzzle where the picture gets clearer with every piece you place correctly. The Picard iteration works similarly. It starts with a simple initial function and, through repeated calculations, gets closer and closer to the true solution. This makes it not only a powerful tool, but also an intuitive way to approach problems in differential equations. So, grab your pencil and notebook, and let's dive into how this method works and why it's so effective. A differential equation is an equation that relates an unknown function to its derivatives. The specific type of differential equation we're focusing on is called a first-order differential equation. Here's its general form. It's called a first-order differential equation because it involves only the first derivative of the unknown function. When solving a first-order differential equation, we often deal with an initial value problem, or IVP. This means we are not only finding a solution to the equation but also ensuring that the solution satisfies a given starting value. Picard's theorem tells us that under specific conditions, an IVP for a first-order differential equation has a unique solution. These conditions ensure that, starting from a given point, there is only one possible path the solution can follow, making it both predictable and reliable. Now that we know Picard's theorem guarantees a unique solution for an initial value problem under specific conditions, the next question is, how do we actually find that solution? One approach is through Picard iteration, a method used to approximate the solution. To use this method, we first need to rewrite the initial value problem in its equivalent integral form. This step is essential because Picard iteration works by repeatedly applying this integral form to refine the solution. Each iteration brings us closer to the true solution of the differential equation. Once we have the integral form of the initial value problem, we might think we've already solved it. But there's a challenge. The unknown function, y, is still inside the integral. This means it's not an explicit solution yet. This is where Picard iteration comes in. It's a method for approximating the solution to the problem. Instead of solving it all at once, we construct a sequence of functions that get closer and closer to the true solution. These functions are labeled as. Each function in this sequence is computed using the integral form, and the process is repeated until the sequence converges to the solution. To begin the Picard iteration process, we first need to choose an initial guess for the solution. This initial guess is typically chosen based on the initial condition of the problem. This serves as the starting point for constructing the sequence of approximations. Each subsequent function in the sequence will build on this initial guess, bringing us closer to the actual solution of the differential equation. After choosing our initial guess, y sub 0, the next step is to use the integral form of the differential equation to create the first approximation, y sub 1. We do this by substituting y sub 0 into the integral equation. This gives This process transforms the equation into something we can compute, and y sub 1 becomes our first approximation of the solution. Once we have the first approximation, y sub 1, we repeat the process to create the second approximation, y sub 2. Here, y sub 1 serves as the input function for the integral, and the output, y sub 2, is an even closer approximation of the solution. Each step brings us closer to the true solution. After creating the first and second approximations, we can now describe the general form for the sequence of approximations. This formula is the foundation of Picard iteration. By repeating this process, the sequence y sub n converges to the unique solution of the differential equation. If you're enjoying this video so far, don't forget to like it, share it with others, and subscribe to the channel for more videos like this. If you have any questions or thoughts, drop them in the comments below. We'd love to hear from you. Let's start with an easy example to see Picard iteration in action. Consider the differential equation. For this simple example, the exact solution can also be obtained analytically. This will help us compare the results of the Picard iteration with the true solution as we go through the steps. Now, let's find the exact solution to the differential equation y prime equals y with the initial condition y of 0 equals 2. The key observation here is that the unknown function y and its derivative y prime are the same. This means that the only function that has this property is the exponential function, which grows at the same rate as itself. So, we can start by assuming the solution is of the form. Here, c is a constant that we need to determine. To do this, we use the initial condition y of 0 equals 2. Substituting t equals 0 into the equation, we get This is the solution to the differential equation, and it shows how the function grows exponentially. Now, let's rewrite the differential equation along with its initial condition in integral form. We can rewrite the equation as This transformation is essential for applying the iterative method effectively. Now, let's discuss a small but important change in notation that will help us work with the Picard iteration process. Instead of using the notation y sub n to refer to the nth approximation in the iteration process, we will now use y at n. This helps make it clear that we are working with discrete approximations. This is very common when we deal with iterative methods because it helps us keep track of each step in the approximation process. The first step in applying the Picard iteration method is to determine an initial guess for the solution. This serves as a starting point from which we commence the iteration process. For our initial value problem, the initial guess will be. This initial guess acts as our first approximation in the Picard iteration process, and from here, we will enhance our estimate step by step. Once we have our initial guess, the next step in the Picard iteration process is to find the first approximation to the solution. To do this, we start with the general integral form of the differential equation. Next, we substitute our initial guess into the integral form of the equation. When we evaluate this integral, it provides us with the first approximation. This first approximation represents an improved estimate of the solution. We will continue this process, substituting each subsequent approximation into the integral form to refine our solution further. After obtaining the first approximation, the next step in the Picard iteration process is to find the second approximation. To do this, we substitute the first approximation, 2 plus 2s, into the integral form of the differential equation. Now, when we evaluate this integral, we get. Carrying out the integration. This gives us the second approximation. With each step of the Picard iteration, we get closer to the exact solution of the differential equation. With the second approximation complete, the next step in the Picard iteration process is to estimate the third approximation. We start by substituting the second approximation, 2 plus 2s plus s squared, into the integral form of the differential equation. Now, let's evaluate this integral. Carrying out the integration. This third approximation further improves our estimate of the solution. As we iterate, each step refines the solution, getting closer to the exact answer. Let's take a moment to revisit the exact solution of our differential equation, which we calculated earlier, 2e raised to t. To gain further insight, we will compute the Maclaurin series expansion of this exact solution. A Maclaurin series represents a function as an infinite sum of polynomial terms centered at 0, providing a way to approximate the function near that point. Now, to compute the Maclaurin series for 2e raised to t, we start with the series expansion for e raised to t, which is. From this, we can write the series for 2e raised to t by multiplying each term by 2. Simplifying, we have. If you find this topic intriguing, I encourage you to explore series expansions further through independent study. It's a fundamental tool in mathematics with many practical applications. Now, let's compare our approximate solutions from the Picard iteration process with the Maclaurin series expansion of the exact solution. We observe a clear pattern. The nth approximate solution from Picard iteration matches the first n plus 1 terms of the Maclaurin series. This demonstrates that as we increase the number of iterations, the Picard approximation becomes closer and closer to the exact solution represented by the full Maclaurin series expansion. In the previous slides, we demonstrated how Picard iteration can be effectively applied to initial value problems to obtain numerical solutions. However, It's important to recognize that there are situations where, despite all conditions of Picard's theorem being satisfied, the method may still fail to generate a solution. In the next slide, we will provide an example that highlights such a case and demonstrate how Picard's method may not work as expected. Let's now look at an example of an initial value problem to demonstrate the failure of the Picard iteration method, even when all the conditions of Picard's theorem are satisfied. Consider the differential equation. The function sin y is bounded, meaning it doesn't grow infinitely large. It also satisfies the Lipschitz condition with a constant of 1. Despite these conditions, the Picard iteration may fail to converge to a solution for this differential equation, and we will explore why in the following slides. Let's begin by writing the integral form of the initial value problem, which will allow us to compute the Picard iterations. The general integral form is given by. This is the equation we will use for our Picard iterations. Now, for our initial guess, we have Now, let's compute the first approximation in the Picard iteration process. We already have the integral form of the differential equation. For the first iteration, we use the initial guess. This simplifies to Therefore, the first approximation is. This is just the starting point of the iteration. As we proceed with the next iteration, we will refine this approximation by substituting this result back into the integral. Let's now compute the second approximation in the Picard iteration process. For the second iteration, we will substitute the first approximation into the integral. Simplify it to Thus, the second approximation is Now, let's proceed to compute the third approximation in the Picard iteration process. We start by recalling the integral form. For the third approximation, we insert the second approximation into the integral and simplify it. In the third approximation, the integral cannot be expressed in terms of elementary functions, meaning it does not have a closed-form solution. Although, according to Picard's theorem, we know that this initial value problem has a solution, the Picard iteration method fails to obtain it in this case. Thank you for watching. In our next video, we will explore how to address this issue by using a modified Picard method. Please stay tuned.